Hello viewers, in today's session we are going to solve an important problem from limits, and here we have to evaluate this limit x tends to infinity, sine 2 over x plus cosine 2 over x raised to x, right? So to get the value of this limit, we'll first try to reduce this limit into this indeterminate form, that is 1 raised to infinity. So let us call the value of this limit as L, and in order to reduce this limit into this form, let us make this substitution, that is y is equal to 2 over x, because when x tends to infinity, then this y, it tends to 0, because when x tends to infinity, 1 over x or 2 over x tends to 0, right? So now this limit L can be written in terms of y. So we can now write limit y tends to 0, and we have sine y. For 2 over x we can write y, and then we have cos y, and for x we can now write here xy is equal to 2, so that y is x is equal to 2 over y. So here we have 2 over y. So now here we have two functions. The first one is sine y plus cosine y, and the second function is 2 over y. So let us assume this function as p of y. We have sine y plus cos y, and q of y is equal to 2 over y. So that this limit can now be written as limit y tends to 0, and here we have p of y raised to q of y, right? So now let us find out the individual limits of these two functions when y tends to 0. So limit y tends to 0, p of y is given by limit y tends to 0, and here we have sine y plus cos y, and when y tends to 0, then we have here sine 0 plus cos 0, and sine 0 is 0, cos 0 is 1, so here we have a 1. And limit y tends to 0, q of y, so this is a limit y tends to 0, and here we have 2 over y. Now when y tends to 0, then 2 over y tends to infinity, right? So this limit, that is limit y tends to 0, p of y raised to q of y, it tends to that is 1 raised to infinity, which is an indeterminate form. So whenever we have this type of form, that is 1 raised to infinity, then the value of these type of limits can be directly written as e raised to limit y tends to 0, and here we have q of y, and then we multiply q of y by p of y minus 1. So here we have the direct result, right? So in general, we can say that if we have limit y tends to say a, and here we have p y raised to q of y, and if limit y tends to a, p of y tends to 1, and limit y tends to a, q of y tends to infinity, that is this limit tends to 1 raised to infinity, then the value of this type of limit can be written as limit, here we can write the exponential number e, then we have limit y tends to a, and then we write q of y times here we have a p of y minus 1. So now here the value of a is 0. So we can now write e raised to limit y tends to 0. Q of y is 2 over y, and then p of y is sine y plus cos y, and then we have minus 1. So we can now take this 2 in front of this limit notation. So we have 2 times limit y tends to 0, and we have sine y plus cos y minus 1 divided by y. So now we have to find out the value of this limit. So now to get the value of this limit, we can make use of L'Hopital's rule. Now here we have limit y tends to 0. So if we take y is equal to 0 in the numerator and denominator, then we have sine 0 plus cos 0 minus 1 over 0. Sine 0 is 0, cos 0 is 1, and we have here a 0 over 0 form, right? So using L'Hopital's rule, we can now differentiate the numerator and denominator. So the value of this limit can be written as e raised to 2 times limit y tends to 0, and we have the derivative of the numerator, and then we can now write here the derivative of denominator. So we have e raised to 2 times limit y tends to 0. The derivative of sine y is cos y, and here the derivative of cosine y is minus sine y. Then the derivative of 1 is 0, and here the derivative of y with respect to y is 1. So we have e raised to 2 times limit y tends to 0 cos y minus sine y. So now we have e raised to 2 times limit y tends to 0 cos y minus sine y. So here we can now take y is equal to 0. So we have cos 0 minus sine 0. So this is e raised to 2 times cos 0 is 1, sine 0 is 0. So this is e raised to 2 times 1, that is e square, right? So the value of this limit is equal to e square. Hello viewers, in today's session we are going to discuss a very important and conceptual problem from continuity and differentiability of functions. And here in this session we are going to discuss the continuity and differentiability of this function f of x, that is the product of two functions x cube and the signum function, that is signum of x. And we have to discuss the continuity and differentiability of this function at this point x is equal to 0, right? So let us first see the continuity of this function at this point, and then we'll see whether this function is derivable at x is equal to 0 or not. So let us start. So now to discuss the continuity of this function at x is equal to 0, we'll find out the right hand limit, and then the left hand limit, and then the value of the function at this point, that is x is equal to 0. And then we'll see whether the right hand limit is equal to the left hand limit, and both these limits are equal to the value of the function at this point. So let us first find the right hand limit. So the notation for the right hand limit is limit, and here we have x tends to 0. Here we put a positive sign, and here we have f of x, right? So now here we'll take x is equal to 0 plus h, where h is a positive quantity, that is h is greater than 0. So we have when x tends to 0, then obviously h tends to 0. So now writing this limit in terms of h, that is x is equal to 0 plus h, that is h. We have limit for x tends to 0 positive, we can now write h tends to 0, and for f of x we can now write x is equal to 0 plus h, that is h. So now we have limit h tends to 0, and f of h can be obtained by replacing x by h in the function. So we have h cube, and here we have a signum of h, right? Okay, so now we have to evaluate this limit, that is h cube times signum of h. So now we can write this limit as limit h tends to 0, and here we have h cube, and then we have limit h tends to 0 signum of h, right? So here we have used this result, that is limit x tends to say a, and if we have the product of two functions, then this limit is given by limit x tends to a f of x, and then we multiply it with limit x tends to a g of x. Okay, so now here let us first define the signum function, and signum function is defined like this: signum of x is equal to positive 1 whenever x is greater than 0, signum of x is 0 when x is equal to 0, and minus 1 when x is less than 0. So now here this limit is simply a 0 cube, because taking h is equal to 0 over here, and then here this limit, that is limit h tends to 0, signum of h is equal to limit h tends to 0, and here we have 1, right? Because h is a positive quantity, and whenever x is greater than 0, then signum of x is equal to plus 1. So here signum of h has the value 1. So now this limit is independent of h, then we can now write here 0, and this is simply 1. So here we have a 0. So the right hand limit of this function at x is equal to 0 is equal to 0. So now let us find out the left hand limit. So the notation for left hand limit is limit, and here we have x tends to 0, and here we put a negative sign, and here we have f of x. So now here we'll take x is equal to 0 minus h, that is simply minus h, and when x tends to 0, from the left of x is equal to 0, then h tends to 0, and obviously h is a positive quantity, that is greater than 0. So now left hand limit can be written in terms of h as limit h tends to 0, and here we have f of minus h, x is minus h. Okay, so now we can write limit h tends to 0, f of minus h can be obtained by replacing x by minus h. So we have minus h cube, and here we have signum of minus h. So now here we have a limit h tends to 0. Minus h cube is simply minus h cube, and here we have signum of minus h. So now we can take this negative sign in front of a limit notation, and we have limit h tends to 0 h cube, and then we have limit h tends to 0 and signum of minus h, right? So here we have used this result. So now we have minus, here h tends to 0 gives us a 0 cube, and here we have limit h tends to 0, and signum of minus h is equal to minus 1, because h is greater than 0, So minus h is less than 0. So when x is less than 0, then signum of x is equal to minus 1. So here we have minus h less than 0. So signum of minus h should be equal to minus 1. So now here we have 0. So this entire term is now 0. So this is equal to 0, right? Okay, so the left hand limit of this function when x approaches to 0 is also equal to 0. Now f of 0 is given by taking x is equal to 0 in the function. So we have a 0 cube and then signum of 0. So now this is 0 and signum of 0 is 0, because when x is equal to 0, then signum of 0 is equal to 0. So here we have 0. So now we see that the right hand limit is equal to 0. The left hand limit is also equal to 0, and the value of the function at x is equal to 0 is also equal to 0. So here the right hand limit is equal to the left hand limit, and this is further equal to the value of the function at x is equal to 0. So the condition for the continuity of a function at a given point in its domain is that the right hand limit and the left hand limit both should be finite, and they should exist, and they should be equal to each other. And moreover, the both sided limit should be equal to the value of the function at the given point. So here we conclude that this function for this function, right hand limit is equal to 0, left hand limit is equal to 0, and f of 0 is also equal to 0. So all these three quantities are equal to each other. Hence, this function is continuous at x is equal to 0. So now let us discuss the differentiability of this function at x is equal to 0. So for this, we have to find out the left hand derivative and the right hand derivative of this function at x is equal to 0. And if right hand derivative and left hand derivative both exist, and they are finite, and they are equal to each other, then we can claim that this function f of x is differentiable at x is equal to 0. So let us first find out the right hand derivative. So the right hand derivative is defined by this limit, that is limit h tends to 0, and here we have f of a plus h minus f of a, and here we have h. So the right hand derivative of the function at some point x is equal to a is defined by this limit h tends to 0, f of a plus h minus f of a divided by h, and here the value of a is 0, and the notation for a right hand derivative is f prime, and here we have a, and here we put a positive sign. So now for a is equal to 0, we have here the limit, that is limit h tends to 0, and we have f of 0 plus h, and then we have f of 0 divided by h. So we have limit h tends to 0, and here we have f of h and f of 0 divided by h. So now we can write here f of h as h cube and signum of h. So replacing x by h. Okay, and here f of 0, as we have just calculated, f of 0 is equal to 0, and here we have h. So now we can simplify it, and we have h cube and signum of h divided by h, and here this h and this h get cancelled, and we have limit h tends to 0 and h square, and here we have signum of h, and remember h is greater than 0, that is h is a positive quantity, right? So when h is positive quantity, that is x is greater than 0, then signum of x is 1. So signum of uh, positive h, that is signum of h, or we can simply write it as h. So signum of h is equal to plus 1. So we have limit h tends to 0, h square times 1, and here the limit is now limit h tends to 0, h square. So this is 0 square, that is equal to 0. So the right hand derivative of this function at x is equal to 0 is equal to 0. So now let us find out the left hand derivative. So the notation for left hand derivative is f prime, and here we have a, and we put a negative sign over a, and this is the left hand derivative is defined by this limit h tends to 0. We have f of a minus h minus f of a divided by minus h. So here our a is 0, and this quantity h is greater than 0, or this is positive. So now taking a is equal to 0, we have limit h tends to 0, f of 0 minus h minus f of 0 divided by minus h. So this is limit h tends to 0, f of minus h, and f of 0 is equal to 0, and here we have minus h. So this is limit h tends to 0, and f of minus h can be obtained by replacing x by minus h. So we have minus h cube, and here we have signum of minus h, and here we have minus h. So now we can write limit h tends to 0, and minus h cube is minus h cube, and here signum of minus h, and here we have minus h. So now again from the definition, signum of minus h is equal to minus 1, because h is greater than 0, so minus h is less than 0. So this is a negative quantity, and whenever this x is less than 0 or negative, then signum of x takes the value minus 1. So now we have limit h tends to 0, and here minus and minus get cancelled, and we have h square, and signum of minus h is equal to minus 1. So we have minus limit h tends to 0 h square, and taking h is equal to 0, we have here equal to, this limit is equal to 0. So the left hand derivative of this function at x is equal to 0 is equal to 0. So now we see that the right hand derivative is it exists and it is finite and it is equal to 0, and the left hand derivative is also finite and it exists and it is equal to 0. So both the derivatives are finite and they are equal to each other. That is, right hand derivative is equal to the left hand derivative, and it is equal to 0, right? So we can also write it as f prime. Here we have 0 plus, and here we have f prime and 0 minus, and both the derivatives are equal to 0. So we can now claim that this function is differentiable at x is equal to 0, because both sided derivatives they are finite and they exist and they are equal to each other. Hello viewers, in today's session we are going to discuss another important and conceptual problem from domain of functions, and in this session we are going to find out the domain of this function f of x, that is equal to 3 times sine inverse, and here we have the greatest integer of 1 plus 3x over 5. So this notation, that is the symbol, the square brackets denotes the greatest integer function, right? So here we'll find out the domain of this function by using an important property of greatest integer function, right? And this problem is going to be an easy problem, and let us see how we can find out the domain of this function using an important property of greatest integer function. So let us start. So now let us take this expression which is inside the square brackets as p. So let us take p as 1 plus 3x over 5. So now we can write this function as 3 times sine inverse of greatest integer of p, right? Now see, here we have the inverse sine function. So we'll first apply the properties of sine inverse function, that is the domain of sine inverse function. And we know that from inverse trigonometric functions, if we have sine inverse theta, then the principal value branch of sine inverse theta lies in the interval that is minus pi by 2 to pi by 2, provided here this theta, it belongs to this interval that is minus 1 to 1. So we can now write theta is greater than or equal to minus 1 but less than or equal to 1, right? Okay, so now first we'll apply this concept. So here this theta may be taken as greatest integer of p. So here we have the first condition, that is greatest integer of p should be greater than or equal to minus 1 but less than or equal to 1. So this is the first condition while finding out the domain of this function, right? Okay, so now from here we'll apply an important property of greatest integer function, and the property goes like this. If we have a real number, say p, and if we take the greatest integer of this p, and the greatest integer of p, it lies between minus n and n, where p belongs to the set of real numbers, and here this n, it belongs to some integer, right? So here when we have greatest integer of p greater than or equal to minus n and less than or equal to n, where p belongs to r and n belongs to z, then this p, that is this real number p, it should lie, that is it is greater than or equal to minus n but less than n plus 1, right? So here we'll make use of this property, right? And now if we take this inequality, and if we compare this inequality with this one, then the value of n is equal to 1, because here we have minus 1 and here we have 1, right? So n is equal to 1 and p is 1 plus 3x over 5. So now we have minus 1 less than or equal to greatest integer of 1 plus 3x over 5, and here we have 1. So now the value of p is 1 plus 3x over 5. So now substituting the value of p in this inequality, we have here for n1, and here we have 1 plus 3x over 5, and here we have n is 1, so we have 1 plus 1. So now we can also write this inequality as minus 1. Here we have 1 plus 3x over 5, and here we have 1 plus 1, 2. So let us now multiply throughout by 5. So we have here minus 5, then we have 1 plus 3x. Here 5 and 5 get cancelled, and here we have 10. So let us subtract 1. Throughout we have here 3x, and here we have 10 minus 1. So this is minus 6. Here we have 3x, and here we have 9. Now let us divide throughout by 3. So we have minus 2, and here we have simply x, and here we have 3, right? So from this inequality we can conclude that the valid values of x for which this function is defined, that is the domain of this function f of x, it should be given by this interval which is closed from the left and open from the right. So here 3 is not included, right? So we have minus 2, and here we have 3. So the domain of this function is given by this interval, that is from minus 2 to 3, where minus 2 is included and 3 is excluded. So now let us draw the real number line here. We have minus infinity, and here we have plus infinity, and here we have minus 2, and here we have 3, right? And here minus 2 is included. So here we have a dark circle, and here 3 is not included. So here we can encircle this 3. So the domain is represented by this region minus 2 to 3, right? So let us verify that here this interval represents the domain of this function by taking some particular values, right? Okay, so let us first take x is equal to minus 2, and let us see whether x is equal to minus 2 is in the domain of f of x, right? So here we are simply verifying our result by taking some particular values. So here for x is equal to minus 2, this expression, that is greatest integer of 1 plus 3x over 5, is equal to greatest integer of 1 plus 3 times minus 2, and here we have 5. So this is 1 minus 6 over 5, and here we have minus 5 over 5, and this is minus 1, right? So greatest integer of an integer is the integer itself, so we have minus 1, and here we have now 3 times sine inverse of minus 1, because the value of greatest integer of 1 plus 3x over 5 is minus 1 for x is equal to minus 2, and it is perfectly true, because here this minus 1, it lies in the interval that is from minus 1 to 1, that is minus 1 in the domain of sine inverse function, right? So x is equal to minus 2 is verified. Now let us take x is equal to 3. So now let us take x is equal to 3. So taking x is equal to 3, here we have 1 plus 3 times minus, here we have 3, and here we have 5. So this is 1 plus 9 over 5, and here we have 10 over 5, and this is greatest integer of 2, and the greatest integer of 2 is simply 2. So now for x is equal to 3, the value of greatest integer of 1 plus 3x over 5 is equal to 2. So now here we can now write 3 times sine inverse of 2, and here this 2 is not included in the domain of sine inverse function, because the sine inverse function has the domain that is from minus 1 to 1. So this value has to be in between minus 1 and 1, that is 2 is not lying in this interval, right? So here we have to exclude x is equal to 3 because it is not in the domain of, that is this expression, that is 2 is not in the domain of sine inverse function. So now let us take one more value. So here we can take a value of x which lies between -2 and 3, and let us take x is equal to say half, right? Then greatest integer of 1 plus 3x over 5 gives us 1 plus 3 times half, and here we have 5. So this is 1 plus 3 over 2, which is 2 plus 3 over 10, right? And here we have 3 plus 2 is 5, and here we have 10, and here we have half, and this is 0 0.5, and the greatest integer of 0 0.5 is 0 by definition of greatest integer function, right? And when x is equal to half, then the value of this greatest integer of 1 plus 3x over 5 is 0. So now here we have 3 times sine inverse of 0, and this 0 obviously it lies in the domain of sine inverse function. So 0 lies in the interval -1 to 1. So here x is equal to half is acceptable, right? So viewers, this is how, by using this property of greatest integer function, we can easily find out the domain of these kind of functions. Hello viewers, in today's session we are going to discuss another important and conceptual problem from derivatives. And here we have a problem where the greatest integer function is involved. So we have to find the value of the derivative of this function f of x at this point, that is x is equal to square root of 2 pi, when the function f of x is equal to sine, and here we have pi by 2 times the greatest integer of x plus 1 minus x square, if x belongs to this open interval, that is 3 comma 4, right? So let us see how we can find out the value of the derivative of this function at this desired point, that is square root of 2 pi, right? So here we'll simply make use of the definition of greatest integer function to solve this problem, and in addition to this we'll also make use of some concepts from trigonometry. So now let us first try to get rid of this greatest integer function, that is greatest integer of x plus 1. So we can remove, or we can get rid of this greatest integer function here by using this statement, that is the x belonging to the interval 3 comma 4. So x belongs to this open interval 3 comma 4, so we can also write this as x greater than 3 but less than 4. And here we have greatest integer of x plus 1. So x plus 1 can be obtained if we add 1 throughout this inequality. So adding 1 throughout this inequality, we have 3 plus 1, then we have x plus 1, and here we have 4 plus 1. So this is 3 plus 1 4, this is x plus 1, and here we have 5. Now see, this inequality suggests that x plus 1, it lies between 4 and 5. So this is our real number line, and here we have 3 and so on, and x plus 1, it lies between 4 and 5. So the greatest integer of x plus 1 is given by 4, right? So the value of greatest integer of x plus 1 is equal to 4 when x is greater than 3 but less than 4. So now we can replace this greatest integer of x plus 1 by 4. So now we can write the function f of x as a sine. We have pi by 2, and here we can now write 4, and here we have x square. So this is sine, and here we have 2. So this is 2 pi minus x square. Now from trigonometry we know that sine 2 pi minus theta is given by minus sine theta. So here theta is x square, so we have minus sine x square. So our function f of x is now equal to minus sine x square when x belongs to this interval, that is 3 comma 4. So now let us differentiate f of x. So we have d by dx of sine x square, and the derivative of sine function is cosine function. So we have cos x square, and by chain rule we have to differentiate x square, and here we have minus cos x square, and x the derivative of x square is 2x. So we have minus 2x cos x square as the derivative of f of x. So now to get the value of f prime of square root of 2 pi, let us substitute x is equal to root 2 pi. So we have here square root of 2 pi minus 2 times square root of 2 pi, and here we have cos root 2 pi, and here we have square. So now we can write here minus 2 times square root of pi, and here we have cos square of square root of 2 pi is simply 2 pi, because here we have 2 pi raised to half, and then we have the square. So 2 and 2 get cancelled, and we are left with 2 pi. Now from trigonometry we know that cos 2 pi is equal to plus 1. So here we have now minus 2 times square root of 2 pi times 1. Cos 2 pi is plus 1. So the value of f prime of square root of 2 pi is given by minus 2 times square root of 2 pi. So this is the value of this expression, that is f prime of square root of 2 pi.